So speaking of encapsulation, let's think about a typical program and what happens in computer memory and during the execution of a certain application. All right, so we have an area of memory, right? We have lots of memory on our devices nowadays, and that's great. And perhaps somewhere on disk, right, which is very typical, we have some kind of executable program which sits there and is ready to be loaded for execution. So when this program is getting loaded into memory right here, it will be giving some space in computer memory, and these little lines represent, in my view right here, some executable code, right? So some kind of set of instructions that can be understood by your virtual machine in Java or directly by the CPU if this program is written in a native code. Like if the program was written in C or C++, for instance, compiled, so it gets compiled to a real code, real CPU instructions that can be directly understood by the CPU. So once the program gets loaded into memory, so this is our representation of memory, perhaps, right? So then in this memory, the program occupies some space, and what happens next that the operating system, which exists also somewhere in memory, right, in a certain area of memory, but I don't want to add too much detail of that. So what it does, it invokes our program simply by calling a place in this program, which normally has a name similar to something like main. You know, there's a main method in your Java application, and there is certainly main function in your C program or C++ as well. And if I want to zoom into this place in the entire application, so here's perhaps as the a part of the program which is your main function or main method in Java. As soon as it gets invoked by the operating system. So it begins to execute, right? So somewhere here at the top of this program, it begins to execute, and it will continue to execute. But before it does anything, the first thing that it does, it actually allocates some space for its local variables here on something we call a program stack. Which is essentially a place, a temporary space in memory where the local variables are going to be housed, right? So we will call this a stack frame. Stack frame is a popular name for this piece of memory that our main function or method is going to use to house its local variables, because variables don't mix with the actual code. The variables have to be kept in a separate area in memory, right? And so if this function makes a call to another function, right, which could be, again, we can kind of picture that someplace there's another function that gets called. Perhaps we can call it initialize global variables, something like that. Right, so we have this other function that gets invoked. Again, before it begins to execute at the very top, what it does, it allocates another stack frame in memory so that it has place to house its local variables. And so every call to a method in Java or to a function in C or C++ requires this allocation, and as soon as this function returns, right, so this function actually goes away and stops executing, and perhaps we return back to our main function or whichever function called it, this place is deallocated. So the memory is actually returned back to the system, and we no longer legally can access it. in order to access it. If we call this function again, right, so if it does get called again, and this repeats itself, the memory for local variables has to be allocated again, and the variables will be initialized as soon as the control passes through declarations of these variables, and the variables will be initialized and continuously used and so forth. Okay, so we have this picture, right? But the local variable, so therefore these local variables that we use a lot, which live in this memory on the stack, the temporary memory area, sometimes they're called stack frames, sometimes, especially on Linux, they're called activation records. It's the same thing. It's basically a little area on the stack where it's housing for the variables. What happens here is that local variables do not survive, the actual duration of a function call. As soon as function returns, naturally local variables disappear. So therefore, as we load this program into memory, there has to be some space allocated for global variables, right? So someplace, this is not necessarily the right sequence of, placement of these segments of memory where things are, but I'll just keep writing on this demonstration. So global variables do survive any sort of function calls. It's simply area of memory allocated for variables that, or data that has to be shared between all parts of the program, right? So any function can refer to a global variable right here in the area allocated for global variables, so the data can be shared between all parts of the program. Okay, so we have these local variables housed by our stack frames, right? So these are local variables which are short-lived, but global variables exist for the duration of the entire application, right? And if we keep writing annotations like this, global variables, local variables, that this is something I would say this is the code segment, right? So segment of memory where the actual code is stored. And code is not your data, it's executable instructions, which can be understood by the CPU. Okay, so we have this arrangement, and so then we begin to think of, of parts of our program, and talking about this analogy with, say, this applications for the heating system, which may include, like I said, the thermostat, right, which is basically the device that can say, let's turn on the heater or turn it off, right? The heater itself, the thermostat may be connected to some kind of temperature sensor, right, which continuously is giving us information about the actual temperature. The heater may have, by the way, the thermostat itself could have internally some kind of a timer, right? So it doesn't want, for example, to signal the heater that the heat should be turned on for just a few seconds. If it's make a decision that the heater should be turned on, it will probably turn on the timer and hold on to that reading, to that state for a longer period of time, perhaps a minute, 2 minutes, 5 minutes, whatever is the program is telling it to do. So there's a thermostat, there's timer, there's a temperature sensor, there's a heater itself, which in itself is probably relying on some timers, right? Because it would not, for instance, if the thermostat constantly tells the heater that it should be on, like all the time, the heater may need to take a break from the heating cycle and will use its own timer to say, well, I will stop after 10 minutes of running to take a break. Okay, so that's could be inherently built into the heater, and so things alike. So it's natural to have these associations and connections between different types of the program. So if you look at this logical relationship between different components of our application, you probably will realize that if we have this temperature sensor, okay, and this temperature sensor gives us information which may be stored in this global variable right here. We simply can say temperature. Right? So we have this global variable temperature which constantly is updated by this temperature sensor. Okay, and at the same time we may have this heater, for instance, which constantly is updating another global variable, which is perhaps basically a seconds or seconds count or something, like some sort of counter that keeps counting how long the heater was actually turned on and running. Right? You'll realize that these two global variables, although they are by nature, by their own nature, although it is available and accessible to all parts of the system because they're global variables. They really should probably be, we can view them as that they need to be separated logically from one another. Okay, and they need to probably, for instance, the heater on its own may not really care about the temperature. And of course, the temperature sensor or thermostat really don't care about this counter of seconds that the heater is using internally for its own, running cycle. Right, so certain data may really be accessed only by specific components of the system. And so this is an interesting observation. And we say that even for the sake of safety and ease of maintenance, we can say that some functions in our system should probably be associated with certain data. Right? So we can think that certain functions should be associated with only certain data. Right? So we have this natural cohesion between the certain pieces of data in certain parts of a running code, the code that can be executed in the system. And if we move in this direction and explore it a little bit more, this is what leads us to encapsulation. Encapsulation simply means grouping of certain variables. I'll give you another example right away: month, day, and year, right? So oftentimes month, day, and year are used together to formulate some kind of calendar date. And it's probably unlikely that you will design a system which deals in completely different parts of the system with years and months. Most likely it's going to be the same component of the system, perhaps a software class that deals specifically with dates and calendars and things that we use in that area. So those three variables, month, day, and year, then should probably stay very close together. They probably have the same life cycle, so they're created at the same time and they're disposed of at the same time. And perhaps all functions which modify, compare, compute different dates, and doing other operations with the components of the date, they're all used together, so they can be used as one component. And we can say that we can formally encapsulate it into one very specific area with some crisp boundaries. Okay? And that also leads us to even higher level of control over that data, is that we might say that once we determine how things should be grouped, we would like to hide the information from the rest of the system. In other words, we would like to create these boundaries. We would like to use these, these boundaries that we create as such that they really cannot be crossed. And so this piece of data really becomes protected inside here, so that it cannot be accessed by other parts of the system, because there's absolutely no reason for other parts of the system to access this particular piece of data except this specific function. Okay. So that's the idea of encapsulation and hiding. And also, this naturally kind of like leads us to another topic, modularity. Modularity basically helps the maintenance, helps understanding, helps simply organizing our programs in multiple files. So modularity also has different types of different kinds of modularization or separation that can be used in the system. So that's, you can see that these things are sort of like interconnected.